Okay, we're back. We're live. It's Monday. Monday. But there's a saving grace on Monday. It's the SOAS show, the School of Ocean and Earth Science and Technology at 1 o'clock or thereabouts every Monday. We're happy to do this. We love this. And today we're going to talk about acidification and how it's coming to a continent near you. Okay?
Very cool.
With three individuals, scientists from SOAS. And as I call your name, would you raise your hand and give a short bio? And keeping in mind that we only have 50 minutes to do this. Okay, I don't know how that works.
That'll be hard for us.
Yeah.
Eric DiCarlo.
Hi, I'm Eric. I'm a professor in the Department of Oceanography, University of Hawaii, working on a variety of environmental geochemistry and most recently focusing on carbon dioxide exchange between the ocean and atmospheres and how that plays into both local, regional, and global issues.
Why are you interested in this area?
Well, to be perfectly honest, my close colleague Fred Mackenzie was the first to get me involved in this. We were doing some other research on land-ocean interactions, and I had a slightly different focus in those days. And Fred, explained to me a few things and said, well, the work that we were doing individually sort of dovetailed, and so we started overlapping a little bit more, and now I've really come all the way over to this side of the research.
You know, when they talk about real estate, you know, the crack on Bishop Street is always, real estate isn't about land, it's about relationships. They talk about law, they say, law, it's not about law books, it's about relationships. Science too, I think.
Yeah, oh, absolutely, absolutely.
Okay, let's go to you, Fred. How did you get it? Bio, please.
No,
Bio, please. Short bio.
How did I get into this? Anyway, I'm Fred Mackenzie. I'm a professor emeritus at the university and a longtime colleague and friend of Eric. And he sort of mentioned how we got hooked up and everything. And to me, it's been a really enjoyable relationship, both from a friendship standpoint and from actually doing some science. Now, in terms of what I do, I am probably now called a global biogeochemist.
Global what?
Biogeochemist.
Okay.
Because my interest is in the Earth, its origin and history, and its future. So I look at the whole system mainly through modeling and try to say what has been ocean composition over time, what has been atmospheric composition over time, and what is the future of all of this. So,
You know, that sounds drear, actually.
it is surreal to some extent.
I mean, it's not like things are going to be better.
No, but I think what you have to keep in perspective is if we don't understand the past, it's much more difficult to understand the future. So we need to know what happens in the past in terms of the topics we're going to discuss in order to say something about the future and what predictions we can make for the future.
Yeah.
So I look at the whole spectrum of things.
So when did this area sort of get born? Is this a recent development in American science or in global science?
Well, I think probably with Spontaneous in the late 19th century, when he wrote a paper and recognized the fact if we put carbon dioxide in the atmosphere from human activities, we'll change the temperature. And
that was visionary, because
It
at
was
that
very
point it
visionary.
really wasn't a problem.
it wasn't a problem at that time, much of a problem. And of course, we were burning mainly coal and wood at that time when we talked about the CO2 problem.
Yeah.
So the climate problem really goes back to him in a way, but the ocean acidification part of the whole, the second problem of rising atmospheric carbon dioxide emissions, really started probably in 1970 when a colleague of ours at the Lamont Doherty Institution, Wally Broker, wrote a paper along with another colleague of ours who was from here, actually, Teluli. And he actually recognize the fact if you add carbon dioxide to the atmosphere, you'll end up acidifying the ocean.
SOEST has a very prominent role in this area. Your career has been primarily at SOEST.
No, I spent 16 years at Northwestern University before coming here, but the greater part of my career is here, yes.
So is SOEST a world name in this area?
Absolutely.
Sounds like it is.
Oh, yeah.
It's probably one of the 3 internationally recognized institutions in the country.
Okay, and I guess by exclusion, Pat
We never exclude. We never.
Pat Drupp is here. He's the anchor man.
Yeah, I'm Pat Drupp. I'm a hopefully soon to be finished PhD student, working primarily with, well, Eric's my main advisor and Fred's basically been my co-advisor for the past almost 7 years
What
now.
a treat.
Yeah, it's been great.
And there's humor there too.
What's that?
Humor.
Yeah.
Keeps you healthy.
It does, yeah. And I kind of just lucked into the whole situation. It wasn't something coming into grad school that I was focused on, or I knew a little bit about it, but I just kind of fell into Eric's group, and this has kind of evolved over the last 7 years into something that's been really exciting and fun to be a part of.
So what's your paper about?
What's my what?
Your dissertation.
My dissertation, it focuses on how ocean acidification is affecting the coral reef environment, specifically around Hawaii. We do a lot of work all around Oahu, in Kaneohe Bay, and on the south shore here, off the shore of Honolulu. How that affects mostly sediment interactions. The sediments are really just leftover eroded pieces of the reef, lots of reef rubble. And we look at how the increasing CO2 and the lowering of the pH affects those sediments and how they're going to react, and then how they're reacting now, and then how they're going to react over the next 100 years or so as we keep, if we mitigate the problem or if we continue with this kind of business as usual scenario that we've been following.
It dawns on me, one of the reasons that SOEST is a leading name in this is that we're in Hawaii. Hawaii is a kind of chemical biological laboratory, a weather laboratory, if you will, because we have islands, and then the islands touch the ocean, and where they touch, you can see things happening, like in the reef, and you can make experiments there that you could not make in the North Atlantic.
Well, particularly with respect to coral reefs, that's for sure.
They don't have coral reefs in the
And
North Atlantic.
well, they have deep water corals,
Okay,
but
sorry.
they don't have
Yeah.
coral reefs. And actually, to me, this has been actually a fantastic association between the 3 of us, because Fred brings a global perspective and is able to integrate data over large scales. I'm more of the local and regional. I understand how the system works here, the land-ocean interactions, and then Pat has become quite the expert, not to mention that he does all the work, and Fred and I,
Be the way
He
it
does
is.
all the work.
we
That's
do.
the
We
other
look
line.
at the data. I always kid around when I go out with them. I said, I just drive the boat. These guys do the work, So
Sounds like fun.
They were just
Right, yeah.
demanding more data this morning. So.
yes,
Well, let me ask you some ingenue questions, because that's where I am. What is acidification anyway? How does that work?
go ahead, Pat.
It's actually pretty simple. It's a simple chemistry problem. If you add CO2, carbon dioxide, to the atmosphere, which we're obviously doing a lot of, if you add it to the atmosphere, it's eventually going to dissolve into the oceans.
By rain. Rain will
that?
drop it in?
Just air-sea gas exchange. It's going to just dissolve in. If there's more CO2 in the air than there is in the ocean, just a chemical process will force it right in. And then once CO2 enters the water, it turns into carbonic acid, essentially. And that has all kinds of effects, the main one being that the pH of the water decreases as that happens. So you're literally adding an acidic gas into the water and causing the pH to decline over time, and then that has all kinds of effects on biology and other chemical components of the system.
So that's the culprit, the carbonic acid.
Yeah.
Yeah, so the acidification has been well documented in Hawaiian waters. Actually, I think Pat has a good slide that demonstrates that over a number of
Why don't we
years.
show that?
Yeah, that's
This,
yeah.
this
And
one.
right there.
All right.
So this
Sure.
particular
What
slide,
is that now?
so on the upper panel, what you're seeing is the annual oscillations of carbon dioxide and how, so you have a winter high in the northern hemisphere and then a summer low because it's taken up by plants, and then it oscillates. But what we see is a long-term rising trend, which is due largely to the anthropogenic or human emissions to the atmosphere. And then the lower panel basically shows the corresponding effect on the pH, which is a measure of the amount of hydrogen ion or the acidity of the oceans, and the oscillations go in the opposite direction. So this record here is from the 1980s through a few years ago, and the long-term trend is down, which is more acidification. And that trend continues to this year, although this diagram is, only through a few years.
Something you said really caught me, though, is when during the season where the plants are growing more, then there's less carbon in the air. They eat the carbon.
Right, because the plants photosynthesize, and so they absorb carbon dioxide. And then in the winter in the northern hemisphere, when the plant life basically hibernates, deciduous trees, they are not removing that carbon dioxide from the atmosphere, and then everything else is respiring, breathing like us, and so they're putting carbon dioxide back in.
But that suggests one thing about the plants. I mean, in Hawaii we have plants all year round. So if we were talking about a sort of limited atmosphere in Hawaii, we'd have the benefit of the plants eating the carbon all year long. But this is not a limited platform. This is global.
This is global.
So
and I
around
think
the
that,
world, you have plants with seasons.
I think what we really should think about is the atmospheric carbon dioxide concentration through time at this point, because it really goes back to Charles Keeling, who was a visionary here in Hawaii, in setting up the Mauna Loa Observatory to continuously measure carbon dioxide in the atmosphere since, I think you have...
Yeah,
we actually
have
the
the CO2 record back in time.
Yeah.
Oh, let's look
It's
at
up
that.
here.
Yeah.
So what is this now?
So this shows the atmospheric CO2 record seen at the Mauna Loa Observatory from 1958 to 2012, is it? Or-
Yeah, that's the top left
The upper
panel.
left panel is
upper left
from
panel.
1958 to present, and then the lower left panel is going back to about 1750, right when we first started burning fossil fuels for energy, and then the panel on the right shows that, and then going back 400,000 years. And so what you can see from that is that the levels that we were at pre-industrial levels around 1750 are basically as high as it's ever been for 400,000 years. And we're overshooting that by
And that actually
nearly double.
That actually goes back at least 800,000 years.
Does Al Gore know about this?
Oh, yes.
Yeah, I think he's aware.
He actually showed this in his first
is that right?
big lecture he gave.
Yeah.
So,
Yeah.
Did you see his lecture? Was it about a month
Yes,
ago?
we
Yeah,
did.
yeah, it was
We all
fabulous.
saw
Yeah,
that.
Yeah.
that was a SOS lecture. Actually.
That's right.
Yeah.
Exactly.
Yeah.
So,
Yeah.
the thing you see in this atmospheric CO2 curve is the cycle, the seasonal cycle, and that is mainly controlled by the northern hemispheric forest breathing, sucking in the CO2 in the summer and then basically releasing it in the winter. And that signal is picked up here on Mauna Loa, and also that signal is what we see in surface ocean waters here.
Would this idea about measuring carbon dioxide precede the telescopes up there? Was this the original reason for the observatory in Mauna Kea?
This is Mauna Loa.
It's on
Mauna Loa, sorry.
Yeah.
No.
I didn't think there was anything at Mauna Loa
At
except a cabin.
11,600 feet, there is an observatory.
Oh,
And they've
okay.
been measuring gases there for 50 years.
Yeah,
almost.
that was a meteorological
Yeah.
observatory
It was
there. So it was
meteorological,
not the
yeah.
space observatory, the telescopes that you have on Mauna Kea.
And you get there from the Saddle Road
That's correct.
as
Correct.
you're
And then
crossing.
You go, yeah, then when you get across from the Mauna Kea entrance, you go just a little bit towards Hilo, make a right, and you go right up.
And that road, as I recall, is on the path to the summit.
Correct.
You take that road, you can drive up that road,
Correct.
but then after that you have to walk to the
Yeah,
summit.
11,600 at the sidewalk.
Give or take.
Give it yeah.
So, but I mean, if we know, not to dwell on this, but if we know that plants help, why don't we just make a lot of plants? Wouldn't that help the acidification process?
Well, that is a problem because to make enough forest to really, have an impact on the whole problem is very difficult. These days in particular, when in actual fact, the forests, because of what we're doing to them, contribute carbon dioxide to the atmosphere by deforestation.
We're actually, yeah, I mean, we're cutting about 1 acre per second in the Amazon right now. So
all those
it's a great
trees,
idea to put trees back and let them, but we're doing the opposite just
but
because of what
in the subtropics and tropics, particularly in the developing world, they're cutting down forests for other uses. So this is one of the land use component of this global change. So we're pumping it in from burning fossil fuels, but as you remove forests, usually there's combustion associated with that and a decreased ability to take up the carbon dioxide because those plants are no longer there.
If you had to sort of put it in a priority, I mean, which thing is more deadly for acidification and climate change? Is it cutting the forests down and I guess burning them also, as they do in Brazil, or fossil fuel cars all over the place?
By far the industrial emissions by about almost a factor of 10 to 1.
Yeah.
There are 8 billion tons or so of industrial emissions of CO2 to the atmosphere, and there's only about 1 from land use activities.
So I couldn't tell the scale on that last slide you had, Pat. But that box on the upper left.
The upper left.
Over what period of time is that?
So it goes from 1958 to 2013.
And have we doubled, tripled, quadrupled? I mean, what can you?
We've gone from, it's about 315 up to essentially 400 now. And at the start of the Industrial Revolution, it was about 280. So when we started burning fuel, it was about 280, and we've gone the whole way to 400 now.
This is where that bottom left panel shows that very clearly. A small rise from the 1700s to about 50, 60 years ago, and then just a major, major rise, basically after World War II.
Yeah.
When my wife and I were having dinner with another couple when I heard about Al Gore's movie, and I stood up and I left them there. And I immediately walked over to the Varsity Theater myself to watch that movie. I had to watch that movie.
Good.
Because it scared me so much. Anyway, okay, let's take a short break and recover.
Sounds good.
And then we'll come right back and we'll talk about the exact experiments that you're doing and how you contribute to those charts and graphs. From my far left, it's Pat Drupp, Fred Mackenzie, and Eric DiCarlo from SOEST. This is the SOEST Hour every Monday. Today we're talking about acidification and how it is coming to a continent near you. I guess that really means it's coming everywhere.
That's correct.
We'll be
Absolutely.
We'll be right back.
Hello, I'm Martin Despang, and I'm the host together with the one and only Ali Amashta, and our show is called Urban Transcendence. And Urban Transcendence is about identifying where we have a unique situation of a vibrant city in one of the most beautiful natural environments. So how these two can coincide, sometimes conflict, how they could find reciprocity in the 21st century is what we're excited about. And we're planning on bringing in a diverse body of guests, both from the arts and the science and the established and the wise and the emerging generation. So hope you will join us. We'll always be on Thursdays from 1 to 2 p.m. Thank you very much. Hello, I'm Martin Despang.
You're on the SOEST Hour. I'm Jay Fidell. We're talking about acidification and how it is coming to a continent near you with Pat Drupp, Eric DiCarlo, Fred Mackenzie. So I guess what I'd like to do is sort of drill down on how you make your measurements. You know, Fred was talking about modeling, and we've talked with so many people from the university about modeling. So I think we get that. I'll tell you what comes to mind. It's a huge computer thing. I think that's it.
Takes a little more than that.
It's a spreadsheet with a zillion fields, and you're going to use David Lasner's new building over there, right?
Right.
There you
You're
go.
going to model.
Is he the new president?
I don't know.
But it's still a new building, the new
still a new
IT
building.
building,
Whatever,
right?
but
I think he'll visit it anyway, whatever happens. He's so invested in that building. 42 million, was it?
Yeah.
It's quite a bit of money, yeah.
Yeah. So, modeling has got to be one of the big tools these days in all of this kind of SOS type of research, and you've got to have a computer programmer, I guess, and you've got to have a computer which can handle a very big database.
Well, Pat is going to create a model. He's in the process of doing it right now, and he's just on his little laptop, basically.
Yeah. I've always teased Fred about the modeling aspect of things, but it really requires a sound understanding of all the processes, what the reservoirs are, in other words, the compartments where the different constituents you're looking at reside and how they transfer from one to another.
What's a reservoir?
A reservoir would be like a box, like your bank account.
Okay.
Okay. When you when you write a check, you're transferring money from your account to whatever store you have purchased some materials from, and it's very important to be able to have measurements that can then be compared to the output of the models, so that you can see how accurate your modeling effort has been, whether you are accounting for all the things that take place. And Pat's actually doing both. Pat's doing all the measurements now, and he's developing a new model as well.
Trying to develop a new model, yeah.
So, I guess what I'm coming to, I think in my mind, I'm learning from all you guys every week. After a while, it sinks in. But modeling is like always there. You always want to do modeling. It is the scientific literature, so to speak. I mean, it's the basic product of your work, modeling.
Well, I think if you do not develop a model, a problem you definitely have in earth science in general, earth and ocean, is that you can't make predictions very well.
Yeah.
So modeling really is what constrains our predictions of the future.
Yeah.
And all of the Intergovernmental Panel Climate Change science volumes, a lot of it is the predictions are based on modeling.
And so if you want to evaluate another scientist from somewhere else, his work in this area, first thing you do is look at the way that modeling is done. You look at the assumptions, you look at the elements of how you make a model and see if you like the model, right?
And then you try to, if possible, replicate the other person's model output. And that is a difficulty.
Yeah.
Using the same data.
Using the same data.
Yeah.
And in there's a lot of formulae, right?
Yeah, I mean,
your parameters are really algorithms.
Yeah, like Eric said, you've got to figure out how things are moving back and forth between these different reservoirs, for instance, between the open ocean and Kaneohe Bay or something like that. You have a certain amount of carbon in the open ocean, a certain amount of carbon in Kaneohe Bay, and they're moving back and forth through all these different pathways. And you've got to figure out what all those pathways are, and then you've got to figure out how they're moving between those and how fast and what rates, and then how that will change as, say, you acidify the open ocean, what's going to happen.
So a simplest model is one that you have on one of the slides. It shows the different processes that affect carbon dioxide in a reef environment right here. So,
that's the one?
Yeah, that's the particular slide there.
Okay. So what is that telling us?
Well, Pat, why don't you go ahead and explain it?
Well, this is like really basic. It's obviously not a numerical model or anything. It's just kind of showing you the different processes. But in the middle, you can see where it says CO2 in the brackets. That's representing the concentration of carbon dioxide in the water. And then so all the arrows are going in and out and are adding or removing carbon dioxide. So for instance, we have, I mentioned at the beginning, the air-sea gas exchange. So that's just the CO2 that's transferring between the atmosphere and the water.
And that's a physical process.
That's a physical process. And then there's the movement of CO2 between, in this case, a coral reef. So we could imagine Kaneohe Bay, like the barrier reef in Kaneohe. the CO2 that's moving between the reef and then the open ocean. So as the open ocean flushes across the reef. You have other processes. We talked about photosynthesis and respiration. Adding or removing CO2, the photosynthesis is going to remove CO2, and the respiration is going to add it. We have river inputs, so water that's coming in through all the streams. And then the other one that we focus a lot on and is the big part for acidification is the carbonate calcification and dissolution. And so calcification is the process that an organism like a coral creates its hard skeleton, a hard shell, and then dissolution is the opposite process, when that hard shell dissolves back into its chemical components into the water. So,
which one is better than the other?
well, we'd like the corals to be calcifying so that the reefs
so
continue to grow. Yeah. And as we lower the pH, it's harder for that process to happen. That's the big thing that everybody gets at.
And that's one of the big problems, is that some of the models that Fred and his prior students and colleagues have come up with is that they show that basically by the middle of this century, there may be more dissolution going on than there actually is production of calcium carbonate on the reefs. And at that point, you know, if you want to take the sky is falling approach, basically our coral reefs will be dissolving away. So that has a lot of implications from the aesthetic perspective, the ecosystem services, and in Hawaii, with a tourist industry based very largely on our beautiful coral reef environment, that's a very important local concern.
So what about the secondary effect? I mean, so I don't go spearfishing. It's like that Stallone movie where he said they were blowing up a grocery, and we're going to blow up the grocery, and he says, "I don't care, I'll shop here." So, well, you know, I don't go, you know, spearfishing. And I certainly don't walk on coral reefs either. So that's probably a good thing.
Yeah,
that's helpful.
So I learned the hard way. But do I care? I mean, is this going to pop up in some other way that's going to bite me?
Oh yes,
Well,
very definitely. I mean, in terms of the benthic fisheries, for example, if reef accretion does slow down, or even, as Eric said, become negative, that it's not growing as fast as it's dissolving, then the habitat for the benthic fishes will be destroyed, and obviously then, you know, there just will not be as many fish now around. If you destroy the barrier reef, you destroy the source of all the materials for your beaches. So if the barrier reef goes, then all those grains of corals and echinoids and all the other shelled materials are not available for beach supply.
An underwater desert.
It's not just it's not just corals though either. You know, in Hawaii we focus on the corals because they're everywhere and we see them and they're beautiful and they're part of the culture. But it's things like oysters and scallops and anything that makes any marine creature that makes a hard, well not any, but most marine creatures that make a hard shell. The oyster fisheries off the coast of California, or off the coast of Oregon, the Pacific Northwest, were hit hard in the last decade from decreasing pHs that make it hard for the babies, the juveniles, to grow. And the scallops are by basically the same process, and so you could see large die-offs, problems with fisheries, and then it becomes an economic problem also for all those people.
Well, and another one in the Pacific Northwest is that salmon eat these little critters, juvenile salmon eat these little critters that do secrete a calcium carbonate shell, and without those critters around, the juvenile salmon are basically missing a food source. And
Actually,
so that's
Same in the North Atlantic.
In some experiments they were performed on benthic fishes by growing the fishes at ambient carbon dioxide levels, you know, like today, for example, and then at double, the fishes begin their response.
They're stressed.
They start to go crazy. The little clownfish, for example.
So this is happening now.
This is happening.
In
That's
some degree,
correct.
it's happening
Yes.
right
Yes.
now.
Absolutely.
And it's happening worldwide because ocean acidification is a worldwide problem.
Yeah.
And this is not the only place where we monitor OA through time. It's being monitored in the North Atlantic, for example? And how many coastal sites?
Oh, there's probably 20 plus coastal sites now. Part of the NOAA Pacific Marine Environmental Laboratory have a very important carbon dioxide monitoring program, and it's actually one of Fred's ex-students who's the head of the PMEL and with whom we collaborate very closely. And we were the first coastal mooring. They already had open ocean moorings, and we set one up in Kaneohe in 2005. And then in 2008, we've added several others. We added another one in 2011. But that program is very important. And one thing we haven't mentioned is that atmospheric circulation is a global process. So whatever CO2 is being emitted into the atmosphere, it's going to affect all the oceans, basically.
And
so
all
it's
the
not
reefs
just,
everywhere.
That's correct. It's not a local problem. It is a global problem.
Let me go back to that slide, if I may.
The last one?
That one, yeah. So this slide is essentially your analysis of the way things affect each other. It's a, sort of a hypothesis. And then this slide, you get data to sort of fit in the pukas on this slide to sort of verify the degrees, the quantums about how this thing is working. And then you put that data into the model.
Yeah.
And the model confirms, or you want the model to confirm this slide, this drawing.
Yes.
And then from the model, you write a paper. And the paper, the model is in the paper. It's attached to the paper, or parts of it, I guess. And you make a conclusion, a scientific conclusion based on your analysis of that model, and then you publish it. And then you have your PhD. Is that the way it works?
That's the goal, yeah.
That's the last
Just checking.
chapter.
But Pat's been very productive. He's published multiple papers already on the various pieces of work that we've done. So it's been really good. And they focus on different aspects. Some of the measurements we used were looking primarily at phytoplankton productivity. Remember earlier I said that my focus is more on the local/regional, so we were looking at how the inputs from land were affecting what's going on in the ocean, and that was what Pat did on his first paper, and then on another paper he actually looked at how the physical processes on the reefs, the tides, the currents, the winds, and how those affected the carbon dioxide system.
Well, I wanted to ask, so where do you get the data? Do you have to go out there with a little machine and measure the
Show the buoys.
the carbonic acid, was it?
That's correct.
Yeah, well, we're pretty fortunate to have some really nice equipment that not everybody gets to use. You can see on the right side of that screen, there's a buoy offshore of the bright yellow buoy offshore of Honolulu. We have 2 of them there, and then we have 2 more in Kaneohe Bay, and those are actually making measurements every 3 hours continuously of CO2 in both the atmosphere and in the water. And so it doesn't mean we don't have to go out and do anything. They break down and we have to change batteries and fix things and clean them and stuff like that. And then we take samples while we're out there as well to make sure the instruments are actually working properly. But we have this nice network that it gives us this data and it transmits it via satellite once a day, and it's posted online. So anybody could go look at these data, and they're updated every single day.
Your data.
Our
data.
Right.
You are updating for other people through satellites.
Well, actually,
it goes to NOAA, the National Oceanic Atmospheric Administration.
So if you look a little bit closer at that diagram, the top right diagram shows the buoy, and the carbon dioxide measurements and ancillary measurements associated with that are sent directly to PMEL through Iridium satellite.
Qu'est-ce que c'est, Penny?
So PMEL is the Pacific Marine Environmental Laboratory. It's part of NOAA. It's one of their big research labs. And this is where our colleague Chris Sabine and his colleagues are helping us. And then the lower panel shows another instrument under the buoy where we make measurements of chlorophyll, which is what the plants use to photosynthesize. We measure the pH, we measure the turbidity, we also measure oxygen and salinity and temperature. And all of those measurements then go into the various models that Fred and Pat are developing.
But that's here.
And
Yeah,
that's here.
That's
And so the lower
what about
instruments,
all the other places?
we actually, but there's a network of these, and we have multiple colleagues throughout the world who are doing this. And on the lower instruments, all of those water quality measurements, those are made every 20 minutes. And those are posted on a website through the School of Ocean and Earth Science through the PAC-IUS program, Pacific
It's open
Island
to the public,
Ocean
to the
Observatory.
scientific community.
Yeah,
Anyone
and
who
anyone
wants-
can look at those data.
Yeah, if you wanted to see if it was warm enough to not wear a wetsuit or something. I mean, it always is, but
Or,
you
or
can go
more,
look at it.
or
Yeah.
more importantly, on the water quality side, for example, when we have a big rain event and you have turbid plumes, you know, some sediment that comes out into the ocean, the local recreational users could go to that website and see that information. Go, oh, well, maybe I shouldn't go out in the water today because it's all muddy. You know, so there's other utility to the data that we gather.
And
Well,
something, may I make a comment on what Eric just said?
sure.
Because there's a feedback between what happens on land and what happens in the ocean. And one of the big feedbacks is just exactly what Eric was talking about. These plumes of fresh water that come out during storms carry nutrients with them, and they fertilize the ocean surface. And you have phytoplankton blooms, and that sucks the carbon dioxide out of the water. So actually CO2 goes down during those storms.
We have another
Got
slide
a
on
nice
that.
one here? Yeah.
Oh, let's play that one so we can see that.
Yeah, there.
So
Okay.
Pat, why don't you go ahead and explain that for us?
Oh, yeah, there's a lot going on there. But that's
Now,
actually.
where's this from? What
So-
instruments were used? And
So
forth?
these are there's 4 different colors on there, and there's the blue, the big, what looks like a thick line in the back is blue, is from a buoy that we call CRIMP 2. It's the Coral Reef Instrumented Monitoring Platform, and that's out right on the barrier reef in Kaneohe Bay. You can kind of see it in the background picture, and then.
No, every good graph has a background picture.
Yeah, absolutely.
Let's give you context.
Yeah, you got to know where it's at. And then the green and the red are 2 buoys that are off of the south shore of Honolulu. They're both only about 200 meters offshore. One's right offshore from Magic Island at the Alawai Canal in the harbor there, and the other's offshore of Kaka'ako and Koalo Basin. So they're very close to land. And like Fred was just saying, we put them in those 2 spots because the one at Alawai gets a lot more of that fresh water in the turbid. You know, anybody in Hawaii has seen the Alawai after a big rainstorm. A lot of that comes out, and then we see the effects that has on the water right at that buoy. Whereas the other buoy, the red line, which is called Kilo Nalu, doesn't have that same effect. So it's a little more of a background, kind of a control, so we can see what it would look like normally and then what it looks like under these storm conditions. And then the blue in the back, the CRIMP, is on a reef, and you can see there's very large swings, and that's due to all the biological activity that's going on. Like we talked about, there's photosynthesis and respiration, and then the corals are calcifying and dissolving as well.
And that's on a daily basis. You have daily oscillations that are
So
huge.
the scale of that is
It's
actually
the breathing
3
of the
years.
oceans. It's-
That's correct.
Yes, it is, exactly.
Well, okay, I'm really impressed. Not only that you have this, but that you have access to other data all around the world that comes to you from similar installations. And it reminds me of the weather guys that we've talked to from SOAS, which I guess maybe weather is part of your thing too, where, you know, they get data from satellites from anywhere and everywhere where anything is happening in the whole world. And the scientific community allows, you know, everyone access to that. So the science must be moving fast because you have, you know, you don't have to wait on the data. You don't have to go out and get it yourself. It comes to you. And,
You know, 10 years ago, there was something like 15 cumulative publications in ocean acidification. Now there's 1,000.
oh, wow.
Yeah, quite a growth. But what you were commenting about on the data availability, it is fantastic. One thing that we need to emphasize, however, is that when we post data in what we call real time, coming straight out of the machine, those data have not been verified. And so it gives you trends, it gives you an idea of what's going on at the moment, but a huge amount of work goes into looking at those data every year and verifying that the instruments were properly calibrated and so on. So there's a big, big effort done both by our colleagues at PMEL as well as as other people within our research group who look, who make sure the instruments are working properly, collect other, as Pat said, bottle samples where we make similar measurements to verify what is coming off of our instruments.
Well, thank God for graduate students.
Yes, absolutely. We wouldn't survive without them.
No way.
Well, we have only like 3 or 4 minutes left, and I wanted to get into the last topic that we said we were going to discuss, and that is the future. The future in terms of this science, that it ultimately will progress to new levels of, of accuracy and ability to predict. And then, exactly where acidification is going in the world, and whether you make predictions on that. And finally, the last topic, all this in a matter of seconds, is, what about the people out there who don't know anything about this? How are we going to make them, how are we going to raise public awareness about this? Because I think it's going to affect every person on the planet soon enough.
Yeah.
Well,
Fred, you want to tackle that?
Your conclusion is absolutely correct. And I think the only way we can get to the community at large is through education. We just need more education about the subject. And any way we can do it, like, for example, your show is helping to do that. It's helping to make people aware.
You've seen the trailers on this new serial. They don't make movies anymore, they make serials, and because it's sort of more than a movie. It's called The Day After Tomorrow.
Yeah,
it's one of those.
I've seen the movies.
Yes.
Yeah. But I think on a broader issue, the only way to alleviate the problem of ocean acidification globally is to cut down on the carbon dioxide emissions. There's no other way out of it.
Are we doing that?
In the United States, we have been. We actually have been doing that over the last 2 decades. In the globe as a whole, and maybe got some
Yeah, go ahead and
pictures
pull
there.
up those slides.
The globe as a whole, China has overtaken us now in terms of total emissions of carbon dioxide to the atmosphere. But interestingly enough, the Chinese are aware of this problem, and they are trying to do something about it.
And most recently, this morning, President Obama's new rule of carbon emissions for
Let's hear about
coal-fired
that.
power
What did he
plants.
say this morning, and what does it mean?
So the EPA is trying to pass through a regulation that says that by 2030, all existing coal power plants, the emissions by state from all existing coal power plants has to be reduced by 30% based on their 2005 levels. So they can go about that any way they want. There's a lot of flexibility in the rule, which is why, or in the regulation, which is why so many people are excited about it, because it doesn't pigeonhole, you have to use renewables or you have to reduce. And so it allows states to kind of go with what they want. They can increase solar, or they could increase wind power, take advantage of hydroelectric or geothermal, or they can just make smart energy grids and decrease overall electricity consumption. So there's a lot of different ways to go about that. So, I mean, we were talking about it this morning. We were really excited about it. We don't know if it's ever going to actually pass, but it's great kind of that they're really trying to get something through right now, because coal is a huge problem here in the U.S. and in China.
Well, that's what that last diagram showed.
It's cheaper than oil now, again, and so we're moving back to it, even though it's way dirtier than oil or natural gas.
The most dirty fossil fuel.
Yeah.
Well, you'll be able to, assuming this EPA change has some likelihood of success, at least reducing CO2 and acidification, you'll be able to see it, won't you?
He might.
You'll be able to verify.
He might. Eric's correct. I doubt I will.
Oh, it's a
I'm
question
pretty
of
sure
when.
I won't either.
Well, if you guys won't, I won't.
One of the big problems is, the United States is responsible for about 22-23% of the emissions. But then there's the rest of the world that we have to deal with, and that's...
Which may not be as aware of
and
it.
China and India are now overpassing,
China and India are responsible for about 90% of the emissions growth between last year, or between 2012 and 2013. So the U.S. and Europe are, they're trying to do their part, but we kind of caused the problem to begin with, in the past 150 years or so. So it can be kind of hard to sit there and tell China and India, hey, don't use these cheap fuels, when we did the exact same thing to get where we are.
Yeah, it's an ethical issue. Well, you know, the first step in solving the problem is finding out exactly what its dimensions are. That's what you guys are doing. And from there it goes to public education, and from there hopefully to public action.
Well, at least luckily with the newer rule, Pat this morning was mentioning that apparently it has pretty much across the political spectrum, there's about the same amount of support, which is a nice change, right? Usually it's pretty polarized, but you know, it's very partisan, and this one seems to have pretty broad-based support, which is a wonderful thing.
We've come a long way since that day I left the restaurant and went to see the Al Gore movie.
Indeed we have.
Anyway, so to my left, Eric DiCarlo, to his left, Fred Mackenzie, and to his left, Pat Drupp, all from SOWEST, all involved in finding out about acidification and carbon dioxide. The title of our show is Acidification is Coming to a Continent Near You, but probably it's already at a continent near you, because it's everywhere. Here on the SOWEST Hour. Thank you so much, gentlemen.
Thank you, Jay.
Thanks for having us.
Aloha.
It's been a
Come back.
pleasure.
Aloha.